Hi all. Now we will see an important topic, that is array processor. But before going to discuss about array processor, let's try to understand an important concept called memory interleaving. So all of you know about memory interleaving. So the memory interleaving says that if I have a memory, let's assume this is my main memory, and this main memory has been divided into four parts. So the main memory is divided into memory array 1, memory array 2, memory array 3, and memory array 4. So this is memory array 1, memory array 2, memory array 3, and memory array 4. Now if you observe, each of these memory array has its own address register and data register. Each memory array contains a separate address register and data register. So what happens with this address register and data register, this acts as a one separate individual memory entity. So this we have now, it's like we have four main memory components within a single computer. It's something like that, because if you observe, each memory element has its own address register, data register, and this is memory. So it is called one main memory component. So like that, if you see, we have n number of memory elements, and all these memory elements can be accessed in parallel. So all of these memory elements, if I have a memory word, let's assume w1 is here, w2 is here, w3 is here, w4 is here. What are w1, w2, w3, and w4? They are memory words. So if I have w1, w2, w3, and w4, if the processor wants to access these w1, w2, w3, w4, they can be accessed in parallel. So those can be accessed in parallel. So that is the main reason having. So the concept, the advantage behind having memory interleaving is that we should able to access w1, w2, w3, and w4 at same time. That is the goal. We can access these w1, w2, w3, and w4 at same time. That is the major advantage with the concept of memory interleaving. And remember, if you observe here, this also contains, see, all these address registers are connected to address bus in unidirectional way. That means the get address, that address is stored here. Let's assume at address A1 the word W1 is stored, at address A2 W2 is stored, A3 W3 is stored, at A4 W4 is stored. So address bus issues A1 here, A2, A3, A4. Who issues? The processor issues this address. So the address bus just carries that address A1, A2, A3 and A4. So this at A1 W1 is stored, so it is placed in the data register. So at address A2 W2 is placed, so W2 is placed on the data register. Similarly W3 and W4, and all these are sent using data bus. So ultimately what we are trying to do here is we are trying to access all the elements, all the we are trying to access memory array words stored in these memory arrays in parallel at same time, which is very advantageous for vector processing. For vector processing, this is the biggest advantage. So this is the concept of memory interleaving. Now we try to understand what is meant by a array processor. So an array processor is a processor that performs the computations on large arrays of data. So an array processor is a processor that performs computations on large arrays of data. So array processor performs computation on large arrays of data. This you should understand carefully. Now we can see that there are two different types of array processors. One is attached array processor and the second one is SIMD array processor. So we have two types of array processors. One is attached array processor and the second one is SIMD array processor. You know about SIMD. SIMD stands for single instruction and multiple data. This we might have seen in Flint's classification of parallel multiprocessor. So we'll see what is meant by this attached. First you should know that array processor means it's a processor which performs computation on large amount of data or large arrays of data. And we have two different types. One is attached array processor and the second one is SIMD array processor. SIMD stands for single instruction on multiple data. This we have seen in the Flint's classification of architecture. So we see two different types of processors. They are attached array processor and SIMD processor. And all of you know that SIMD stands for single instruction and multiple data. So we can see that SIMD stands for single instruction and multiple data. So what happens here, This attached array processor and SIMD processor are two types of array processors. Now let's try to understand what is meant by attached array processor. So the attached array processor, it is designed as a peripheral for the conventional host computer. So it is designed as a peripheral for a conventional host computer. All of you know about peripheral. So peripheral means like IO device. Also it is defined like an IO device that you can plug and play. What he wants to say that when I say array processor is designed like a peripheral means you can connect to CPU just like an IO device. Just like you connect an IO device to a CPU, in the same way you can connect this attached array processor. The name itself says you can attach it to a CPU, conventional host computer. Its purpose is to enhance the performance of the computer by providing vector processing. So its purpose is to enhance performance of the computer by providing vector processing. So the goal is vector processing. Vector processing means you should be able to work on large set of data. So its purpose is to enhance the performance of the computer by providing, for example, that means if I have a conventional computer, I already bought one conventional computer which performs sequential computing. Then I can attach this array processor so that my conventional computer can be enhanced. My conventional computer performance can be enhanced by providing vector processing capability, because I am attaching a, see, if this is my conventional computer, let's try conventional computer CC. If I attach array processor, what happens? My conventional computer will have the performance of doing computational problems, because now it is equipped with attached array processor. He can do vector processing as well. So it is used for making the conventional computer as powerful as a vector processor. It achieves high performance by means of parallel processing with multiple functional units. So it has multiple functional units. Then by means of its performance, the attached array processor achieves high performance. How? By implementing parallel processing with multiple functional units. Let's try to understand the figure here. So that what figure contains means, so it contains the figure contains attached array processor. This is an attached array processor with host computer. Now this is general purpose computer which has only capability of performing sequential computation. Now it has main memory. Now this is our array processor, which is called attached array processor. and you are connecting this using an IO interface. You are attaching to the CPU by using a IO interface, and this attached IO interface also has one local memory, and there exists a separate memory to memory bus for transferring the data to and from main memory to this local memory. This local memory is for this attached array processor. So the attached array processor has its own memory. You should try to understand that the attached array processor has its own memory that is called local memory, and this local memory can interact with the main memory by using a special bus called high speed memory to memory bus. You should get it out. Bus means it is hardwired in a motherboard. Then how can this local memory connected to? Yes, there are some external wires here. High speed memory bus means they are some external wires, but they are very high speed. So this is, let me repeat once again. This is my general purpose computer, and this general purpose computer is connected to this attached array processor. Attached array processor is connected to this general purpose computer via IO interface. So this is my IO interface. But the specialty is that this attached array processor has its own local memory, and this local memory interacts with the main memory by using high speed memory to memory bus. Now we see, this is called attached processor. Now we see another type of array processor, that is SIMD array processor. SIMD stands for single instruction on multiple data. Remember, when we discuss about Flint's classification of architecture, here we have one control unit which sends one processing element, and this processing element contains multiple data elements. So this you can treat as a memory interleaving. This can be implemented using memory interleaving. For that reason, we discussed about memory interleaving in the very beginning. So the control unit sends one instruction to the processing element, and processing element will do the computation. So we see what is meant by SIMD processor. It is a processor which consists of multiple processing units operating in parallel. It contains multiple processing units. The processing units are synchronized to perform the same task under the control of a common control unit. So we have one control unit, and we have multiple processing element that are connected to multiple data streams. So this is about the processing units are synchronized to perform the same task under the control of common control unit. So here we have a common control unit. Each processor element includes an ALU, a floating point arithmetic unit, and working register. So this is my control unit. there is only one control unit. Let's assume there are processing element 1, processing element 2, processing element 3, and processing element 4. So what happens, this processing element, for each processing element, PE stands for processing element, contains three components. One is ALU, stands for arithmetic and logical unit. Next, floating point arithmetic unit, floating point arithmetic unit, and of course some registers. So the processing element contains three things. One is ALU, floating point arithmetic unit, and register. So each processing element is equipped with these three things. Now let's look at functional diagram SIMD array processor, how it looks like. As I said, so this is the master control unit. So this is like control unit, and these are processing elements. So the common one control unit can control all these processing elements, and the processing elements, each processing element has separate memory which can access, so which can get, each processing unit gets the words from the main memory. Okay, we have here you may get a doubt. Yes, we have more than one processing elements. That's fine, but all should get the data from same common main memory. So for that reason, we can implement memory interleaving in main memory, so that the words comes parallel to this. Their processing elements are ready to process, but they can't process until they fetch the data from the memory. If there is a one common main memory, all processing elements has to wait. So if main memory is implemented with the technique called memory interleaving, yes, then in that case we can achieve parallelism over here. This is called SIMD processor. So this is called SIMD processor, array processor. Remember, we have a single control unit, single main memory, single control unit CU, single main memory, multiple processing element, and here each processing element contains three things. One is ALU, another is floating point arithmetic unit, and third one is register. So this is about SIMD processor, array processor, and you should really understand that this SIMD processor, the most important thing is, as I said, how these words gets from this main memory. That means now you understand better. Now we can divide this main memory into memory array. Memory array 1, memory array 2, 3 and memory array 4. So each memory array has separate address register, data register. So by this way, if processing elements 1 wants to access W1, processing element 2 wants access to W2, processing element 1 W3, and if it wants W4, then so each memory array contains W1, W2, W3 and W4. Then they get this data by using a concept called memory interleaving. So now we'll discuss an important topic, that is advanced processor technology. So as the name suggests, advanced processor, this is very advanced topic related to the technology. Now the goal of this advanced processor technology is to explore novel architectures. Novel architecture means, novel means new. New architecture. What is meant by architecture? Architecture means how processor is organized, how it is divided into multiple processing elements. So to explore new or novel architectures and techniques that will enable the effective exploration, that and some techniques that will enable the effective exploration of the billion transistor chips of the near future. Exploitation of, sorry, that enable the effective exploitation of the billion transistor chips. It's very important to understand these terms. Billions of transistor chips. So here you need to employ the billions of transistor chips, which is not an easy task. You have to employ billions of transistor chips, so in a single processor should have these billions of transistor chips. And for that reason we have to learn the novel. Novel means new, architecture. You have to read new architecture, and this new architecture should support this billions of transistor. So it should support billions of transistors. It's very important to understand what is meant by a novel. Remember, novel means new architecture, and novel means new architecture and some techniques. You have to learn or implement or identify some new techniques. Now we see on Moore's law that will deliver billions of transistors. So there is a law called Moore's law that will deliver a thousands of or billion, not thousands, billions of transistors. So it's really important to know what is meant by Moore's law. Moore's law states that we should know something about Moore's law. It states that number of transistors on a microchip doubles about every 2 years. What Moore's law says, the number of transistors in a microchip doubles every year, about every 2 years. Though the cost of computers is halved, so he is Morse is a scientist in 1960s, and he's the co-founder of Intel. How of you know about Intel, right? He's the co-founder of Intel. Made this observation that becomes Moore's law. Another uh, tenet of the Moore's law says that the growth of the microprocessor is exponential. Remember, the growth of the microprocessor. What is meant by growth of the microprocessor? Microprocessor chip, which is employed with billions of transistors, they are that is increased exponentially. If this year it is 2 power 2, next year 2 power 3, 2 power 4, 2 power 5. This is called exponential growth. So the number of transistors that a microprocessor can accommodate is increased by exponential. This is called Moore's law. So what Moore's law says, let me repeat once again. Moore's law says that number of transistors on a microchip, number of transistors on a microchip doubles every 2 years, though the cost of computers is halved. So experts agree that the computer should reach the physical limit of Moore's law at some point in 2020s. Why we are insisting so much about transistor means the high temperature of the transistor eventually would make it impossible to create smaller circuits. These transistors generate some heat, and the thing is each transistor generates some heat, and you have to employ or deploy billions of transistors in a small microchip, which is a challenging task. This high temperature makes it impossible to create smaller circuits. This is because cooling down the transistors takes more energy than amount of energy that already passes through transistors. So what happening? The amount of energy required for a transistor, if you compare this with the amount of energy required to cool down this transistor, the amount of energy, the energy means power supply required for cooling the temperature that is raised by the transistor is much more greater than the energy required for running the transistor. So the transistor that is required, so the amount of energy required to cool down the processor, to cool down the transistor within the processor, the high amount of energy is required compared to the energy required to run the transistor itself. So it's a challenging task. It has been a challenging task for many years to deploy billions of transistors within a microchip. Since we are discussing about advanced processor technology, you should understand the challenging task is to, if this is my processor, it, it contains billions of, not even million, billions of transistors. And these billions of transistors generates heat. They generate, the billions of transistors generate heat. And if you want to cool this heat, you require much more energy than running of these billions of transistors. It's a big challenging task. Though the transistor generates heat, you have to deploy billions of transistors within the microchip. And the challenge is, if you deploy the billions of transistors within a microchip, it generates a lot of heat and you have to cool it using low energy. So the Moore's law cannot continue forever. He says the number of transistors in a microchip doubles every 2 years. It may not be possible forever. At some point of time, there is a threshold, there is a limitation. Next, we see some strategy. So, how do we make best use of these billions of transistors? Means we can do parallel processing, we can do system on chip, we have to employ novel architecture. So these billions of transistors, deploying is itself a big challenging task. And again, how effectively use, how to make best use of these billions of transistors is again another challenging task. The first thing is that deploying billions of transistors in a microchip is itself a challenging one, and another challenging comes the utilization, effective utilization of these billions of transistors. You can do so many things with billions of transistors, like you can implement parallel processing, you can do systems on chips, you can implement some novel architectures. Now we see the strategy, vision of this advanced processor technology. Industry shifts to multi-core processors. So it's very important to understand the word multi-core processor. So what are these multi-core processors? Example, I have, I used to have dual core, I used to have quad core, now we are using octa core and hexa core. What are these? What are these? First, let me see dual core processor. The very beginning, 10 years back, when you purchase a mobile, you see the specification of that mobile about 10 years back, you might have seen that this word dual core. Dual core means, dual means two. two cores. Divide the processor into two cores, L1 and L2. So the processor having two processing elements. Now you can easily guess what might be the meaning of quad core processor. So what is the meaning of quad core processor? Quad means 4. So divide this processor into 4 processing elements. Divide this processor into 4 processing elements. PE1, PE2, PE3 and PE4. So these are the 4 processing elements. Next I have octa-core processor. Octa-core, octa means 8. So now we divide the processor into 8 processing elements. It contains 8 processing elements. This is nothing but dual core, quad core, octa core. So the industry shifted to multi-core process. Multi-core means it can be dual core, octa core or quad core. So directly addressed by our CMP network, CMP work, and here power or heat is performance limiting. So the goal, okay, you can divide the processor. Someone can ask me a question like, I can divide the processor into some 32 parts or 64 parts. Why only limited to dual, quad, octa or hexa? That means if you divide this processor into cores, you require high performance. You require more power, which generates more heat. Remember, if I divide my processor into some n number of types, you require more power. The more power generates more heat. So more power is a big task. You should use less power so that less heat is generated. Cooling down this heat is not a easy task. It's a very big challenging task, and it's a very vast area which has the scope of doing research. So power or heat is performance limiting. Asynchronous and low power design have growing importance. Asynchronous, you should understand the word asynchronous or asynchronous. Asynchronous means the speed of the sender and receiver need not be same. The synchronous and low power design have growing importance than synchronous. Timing closure is a critical problem. Acceptance of mixed timings and GALs. See, when you deploy these billions of transistors, maintaining the signals, timing signals, again is a big challenging task. Design automation is a vital one. Asynchronous and automation must be competitive. Next, can university groups design state-of-the-art digital silicons? Probably not in conventional processors. Few academic groups still fab digital chips. Is trying to make designs through a fabrication still a good idea? We believe so because reality matters. But the game is very tough indeed. Now you can see buying a single core processor is difficult. Buying a single core processor is very difficult because the Moore's law, what he says, the number of the transistors on a chip doubles for every 2 years. Multi-cores bring fundamental changes of a computer science, applications, programming language, compilers, runtime systems, operating systems, computer everything. Everything has been changed with multi-cores. Let's take example of this processor which has processor graphics, one core, and here second one, two, three, four cores. This is shared cache, system agent and memory controller. These are the memory controller IOs. This is an example of an advanced processor. This is an example of a advanced processor. It contains four cores, core 1, core 2, core 3, core 4, which has shared L2 cache. There is a separate processor for the graphics. So there are so many challenges in advanced processor technology that we will discuss.